Okay, so the next thing that we have here is another function, which is ax plus b raised to the power n, ax plus b raised to the power n times cx plus d raised to the power m, and you want to take the derivative of this function, d by dx of this. So in the previous video, which was a rather lengthy, long video, what we found out was that basically d by dx of ax plus b whole raised to the power n is equal to a times n times ax plus b raised to the power n minus 1. So we showed that this was basically the derivative of ax plus b raised to the power n. And of course here we have the same story, meaning that this is ax plus b raised to the power n, cx plus c raised to the power m, two such functions basically multiplied together. And so we can use the product rule, u times v whole prime is equal to u prime times v plus u v prime, right? So I can write this as u prime. U prime is basically the derivative of this function, which is basically an times ax plus b raised to the power n minus 1 times cx plus d raised to the power m plus the derivative of plus this function, which is this function over here, ax plus b raised to the power n, times the derivative of the second function, which is basically m times c, which is basically m times c times basically cx plus d raised to the power m minus 1. So that's basically the derivative of your function here. So of course you can rearrange this, but eventually that's the derivative of your function. So number 13 is ax plus b raised to the power n minus 1 times cx plus d raised to the power m minus 1. So you can take these out and write this as, for example, so we have ax plus b over here and ax plus b over here. So I can take out ax plus b raised to the power n minus 1, and then this becomes and of course, and I can take cx plus d raised to the power m minus 1 as well, because they are also common, cx plus d raised to the power m minus 1. And then I can write this as, so here I have taken cx plus d raised to ax plus b raised to the power m minus 1. So I have a times n, and then ax plus b raised to the power m minus 1. So there I have nothing over there, just a 1. And then I have cx plus d raised to the power m minus 1, which I can write as cx plus d raised to the power 1 basically. So if I multiply raised to the power 1 times raised to the power m minus 1, I will get raised to the power m, and then plus ax plus b raised to the power m minus 1 times ax plus divided by ax plus b raised to the power n is going to give you ax plus b times mc, and over here you have nothing. So basically that's going to be the derivative of your function. So we have ax plus b raised to the power n minus 1 times cx plus c raised to the power n minus 1, which would be an or na into cx plus d plus mc times ax plus b. So that's basically, but basically the basic thing that you need to know here is this derivative here and the product rule, and other than that it's just rearrangement of the terms here. So number 14 is the sine of x plus a. You have the sine of x plus a. If you have the sine of x plus a, well, I kind of think, I'm not really sure, but based on what I've seen before, you know that d by dx of sine x is equal to cos x. Okay. Now, based on what I've seen before, if you take d by dx of sine of x plus a, you will get cos of x plus a. But I'm not really sure about this, but we can see what happens. I don't know. Let's see. So let's say that you have the sine of x plus a. So you know that basically the only way that you can do this is using the first principle. I don't think there is any other way to do it. So if you have the sine of, if your f of x is equal to the sine of x plus a, then basically you know that based on the first principle, d by dx of f of x, which is equal to f prime of x, is equal to the limit of basically f of x plus h minus f of x over h as h tends to 0. That we already understand. So what that means is that if I calculate f of x plus h here, f of x plus h is equal to basically sine of x plus h plus a, and then f of x, you already know what that is, and h is just h, you don't need to worry about that. So then f prime of x would be equal to the limit of basically f of x plus h, which is sine of x plus h plus a, minus f of x, which is sine of x plus a, divided by h as h tends to 0. And now you need to just calculate this limit. There is nothing more to it than that. Okay, so here basically what you have is nothing but sine x minus sine y. Sine x minus sine y, which is equal to 2 times cos x plus y divided by 2 times sine x minus y divided by 2. Okay. Now, so you can write this as the limit of basically 2 times cos x plus y divided by 2 would be, this would be x. So that's x plus h plus a plus y, which is x plus a, divided by 2. That's 2x plus 2a plus h divided by 2. 2x plus 2a plus h divided by 2. Times sine of x minus y divided by 2. So that is x plus h plus a minus this minus y, which is negative x negative y the negative sign is multiplied by both of these terms. Divided by 2, so x and negative x, a and negative a, so that's h divided by 2. That's h divided by 2, divided by h as h tends to 0. As h tends to 0. Now, what you have here is basically you can write this as the limit of basically sine h divided by 2 divided by h divided by 2 times cos of 2x plus 2a plus h divided by 2, okay, as h tends to 0. And here, actually, no, I'm sorry, doesn't make any sense, whatever. So, limit of this, and so you can write this limit as, limit of sine h divided by 2 divided by h divided by 2 when h tends to 0 times the limit of cos of 2x plus 2a plus h divided by 2 when h tends to 0. Now you know that the limit of sine of x divided by x as x tends to 0 is equal to 1. So then when basically if this is equal to 1, this is also equal to 1. And the reason for that is that you don't need to be worried about the fact that basically here you have x and here you have x sine x divided by x, and here you have sine h divided by 2 by h divided by 2. These are half angles, of course, compared to this. But eventually when h tends to 0, of course h divided by 2 also tends to 0. So when h tends to 0, h divided by 2 also tends to 0. And you can actually rewrite this limit. I mean, if you want to understand this better, let's focus on this part of the limit here. You have the sine of h divided by 2, basically, let's take h divided by 2 in this limit. Let's take h divided by 2 as y. Let's take h divided by 2 as y. Okay? So when h tends to 0, then of course the value of y is going to be close to, very, very close to 0 divided by 2, which is equal to 0. So then y tends to 0, right? And so when h tends to 0, y tends to 0. So I can rewrite this limit as the limit of sine y divided by y, because h divided by 2 is actually equal to y. When y is equal to 0, when y tends to 0, and this is equal to 1. So this limit is equal to 1. Okay. So what that means is that this is basically just equal to 1 times the limit of basically cos of 2x plus 2a plus h whole divided by 2 when h tends to 0. Now when h tends to 0, you can take h as 0, and then this becomes the cos of 2x plus 2a divided by 2, which is the same thing as cos of x plus a. So that means that d by dx of sine x plus a is actually what I said over here, is actually equal to cos of x plus a. Okay, so that is that. Now, I don't know if that happens in the case of other trigonometric functions, because every function is different from every other function from when it comes to trigonometric functions. But I know that basically in the case of sin x and cos x, whatever your angle might be, then this kind of thing works over there. But I don't know about, for example, tan and secant and cosecant and that kind of thing. I don't really know. If you want to basically use that, use it in the case of other trigonometric functions, you need to basically at least solve each case for each of those trigonometric functions and prove at least to yourself that that's the case, and then you can use it. Otherwise, it's not very safe to assume that, it's not at all safe really to assume that if it works in the case of sine and cos, then it's going to work for other trigonometric functions as well. And so the next question over here is basically you have a function over here, cosecant x cot x. Cosecant x cot x, and you want to find the d by dx of this function. So to find the derivative of this function, it's easy, of course, because we have already actually done this. So let me see. We had something over here called differentiation, and here we said that, well, d by dx of cosecant x is equal to negative cosecant x cot x. d by dx of cosecant x is equal to negative cosecant x cot x. And d by dx of cot x is equal to negative cosecant squared x. And of course, you know already about the product rule, u times v whole prime is equal to u prime times v plus u v prime. So you can use these three things in order to calculate this derivative. So you can write this as basically you can write this as the d by dx of cosecant x times cosecant x times cot x times cot x. I put this in brackets to show that this is just the d by dx of cosecant x plus basically cosecant x times d by dx of the cot x, which is equal to, now d by dx of cosecant x is negative cosecant x cot x times cot x plus cosecant x, d by dx of cot x is negative cosecant x, cosecant squared x, of course. So this is the same thing as negative cosecant x cot squared x minus cosecant cube x. And you can simplify this a little bit, of course. For example, let me see how they have written this. I don't know really. Number 15. They have written it as negative cosecant cube x minus cosecant x cot squared x. You can simplify it using all of the things that you know about trigonometric functions. For example, you know that cosecant x is equal to 1 divided by sine x, for example, or you know that basically cot x is equal to, for example, 1 divided by tan x, and you know that tan x is equal to sine x divided by cos x, for example. And you can use all of these over here to see if you can actually simplify this, meaning that if you could basically take a couple of functions out and simplify them if that's possible. Okay, so number 16. Okay, so the next question that we have is we want to find the derivative of d by dx of cos x over 1 plus sine x. Cos x over 1 plus sine x. So it's just simply the quotient rule. So you can write u divided by v whole prime, assuming that these are two functions of x, for example, or any other variable. That would be equal to u prime times v minus u v prime over v squared. Okay. And you know that the derivative of cos x is equal to negative sine x, and you know that the derivative of sine x is equal to cos x. Using these you can differentiate this function. So I can write this as basically u prime. The derivative of cos x is negative sine x times v, which is basically 1 plus sine x. 1 plus sine x. And minus the first function, which is cos x, times the derivative of the second function, which is d by dx of basically 1 plus sine x. Now, of course, you know that this is equal to d by dx of 1 plus d by dx of sine x. Now, this is equal to 0, and this is equal to cos x. So 0 plus cos x, which is just simply cos x. And you want to divide that by 1 plus sine x whole squared. 1 plus sine x whole squared. Now, well, you can write this as negative sine x. You can write this as negative sine x plus minus sine squared x minus cos squared x over 1 plus sine x whole squared, which you can take a negative out of this whole thing. You can write it as basically negative of basically sine x plus sine squared x plus cos squared x over 1 plus sine x whole squared, and then sine squared x plus cos squared x is equal to 1. So that's 1 plus sine x. That is 1 plus sine x. Of course, the negative of that. And here you have 1 plus sine x whole squared. And so you can simplify this as so 1 plus sine x, and then you can cancel that out with the second power of this. So you have negative 1 over 1 plus sine x. That's the derivative of your function. Okay, number 16, negative 1 over 1 plus sin x. Number 17 is sin x plus cos x, sin x plus cos x over sin x minus cos x, and you want to take the derivative of that, d by dx of this function. Again, the same story. You know that u divided by v whole prime is equal to basically u prime times v minus u v prime over v squared d by dx of sin x is equal to cos x d by dx of cos x is equal to negative sin x, and that's all that you need to know here. So then you can write this as basically d by dx of sin x plus cos x times the derivative of times the second function, which is sin x minus cos x minus the first function, which is sin x plus cos x times the derivative of the second function, d by dx of sin x minus cos x, whole divided by v squared, which is sin x minus cos x whole squared. Now, d by dx of sin x plus cos x is simple. So d by dx of sin x plus cos x is the same thing as d by dx of sin x plus d by dx of cos x, which is, well, d by dx of sin x is equal to cos x. D by dx of cos x is negative sin x. That's cos x minus sin x. That's cos x minus sin x. And then you have sin x minus cos x. Okay. And then you have d by dx of sin x minus cos x. D by dx of sin x minus cos x is equal to cos x. D by dx of cos x is equal to negative sin x. Negative into negative is positive, so plus sin x. So that's minus sin x plus cos x times sin x plus cos x. Sin x plus cos x. And then you have sin x minus cos x whole squared in the denominator. So this is and the way that you can simplify this is sin x plus cos x, sin x plus cos x, right? So if I write this as sin x minus cos x, would be, if I take a negative out here, then I would write this as, for example, sin x minus cos x times sin x minus cos x. So that would be a minus b, for example, whole squared minus, and I have a negative out here, that's not important, and minus basically I don't know, a plus b whole squared, something like that. And then I would take this as a squared minus b squared, which would be a squared minus b squared, which would be a minus b into a plus b, which doesn't make, that's, I suppose, number 17. Okay, maybe we can simplify this a little bit. I think we can simplify it. Let's see. Okay, so now what we have here is basically cos x sin x is basically cos x sin x minus cos squared x minus sin squared x minus sin squared x plus sin x cos x, and then over here you have basically negative sin squared x, negative sin x cos x. Of course, while I'm multiplying these together, I'm also multiplying this negative 1 by every term, so you need to be careful about that. So you have negative sin x cos x, negative sin x cos x minus cos squared x, okay, over sin x minus cos x whole squared. Now over here you have sin x cos x, sin x cos x, negative sin x cos x, negative sin x cos x, so you can cancel out these four terms together, and then you have cos squared x, sin squared x, cos squared x, sin squared x. If I take a negative 1 out of the numerator, I will get basically negative of cos squared x plus sin squared x, over here again sin squared x plus cos squared x over sin x minus cos x raised to the second power, and you know that sin squared x plus cos squared x is equal to 1, so this is equal to 2, so that's the same thing as negative 2 over sin x minus cos x whole squared. So that is your answer there, number 17, negative 2 over sin x minus cos x whole squared. And number 18 is secant x minus 1 is d by dx of secant x minus 1 over secant x plus 1. Okay. Now you know that u divided by v whole prime is equal to u prime times v minus uv prime over v squared, and also d by dx of secant x is equal to secant x tan x is equal to secant x tan x. So then I can write this as I can write this as d by dx of secant x minus 1 times the second function, which is secant x plus 1, minus the first function, which is secant x minus 1 times d by dx of the second function, which is basically secant x plus 1. Secant x plus 1 over secant x plus 1 whole squared. Now d by dx of secant x minus 1 is the same thing as, so you know that d by dx of secant x is equal to secant x tan x. Secant x tan x. So that's going to be equal to basically secant x tan x, and this is 0, times secant x plus 1 minus secant x minus 1 times d by dx of secant x plus 1, which is basically secant x tan x, over secant x plus 1 whole squared. Now here what you can do is that you can write this as basically secant squared x tan x, secant squared x tan x plus secant x tan x minus secant squared x tan x, and this is negative secant x tan x times negative is plus secant x tan x, and then you can well, secant squared tan x and secant squared tan x, these two you can cancel out. Secant x tan x over secant x plus 1 whole squared. So this is the same thing as 2 times secant x tan x over secant x plus 1 whole squared. Now secant x tan x could be probably simplified. Secant x tan x is the same thing as, well, secant x is 1 over cos x, and tan x is what? Sin x over cos x. You could write it as sin x over cos squared x, for example, which is not really very helpful. So I think we need to just leave it as it is. Number 18 is 2 secant x tan x over secant x plus 1 whole squared. Number 19 is sine raised to the power n of x. Is sine raised to the power n of x. So if you want to find the derivative of sine raised to the power n of x, how would you do that? So I think we need to just simply use the first principle, meaning that d by dx of f of x is equal to f prime of x is equal to the limit of f of x plus h minus f of x over h when h tends to 0. Now f of x plus h is equal to, well, if f of x is equal to basically sine raised to the power n of x, then f of x plus h is going to be sine raised to the power n of x plus h, which must be a little bit tricky, but let's see what we can do. So then d by dx of, or basically f prime of x, is going to be equal to the limit of f of x plus h, which is sine raised to the power n of x plus h, minus sine x over h as h tends to 0. As h tends to 0, as h tends to 0 is equal to we have no formula for this. We don't have any formula for this. So how do we do that? Okay, so now what we need to do in order to solve this problem is actually a little bit, it is a little bit complicated, and not really complicated, but it has essentially a few steps that you need to understand. So now suppose that, of course, I do not know what is the sine raised to the power n of x plus h. I don't have any formulas for that, and the problem is that now normally what we would do, what we did in the case of other limits, we had, for example, the limit of, for example, some x of sine of, for example, some angle, for example, minus sine of some other angle, divided by h, for example, as h tended to 0. So as h tends to 0, of course, the denominator becomes 0, and you would get something divided by 0, which is not defined. So you need to somehow get rid of this h from the denominator. So, and over here you have no, and basically we had, for example, this formula, like, for example, sine x minus, for example, sine y is equal to, for example, 2 times cos, for example, x plus y divided by 2 times, for example, sine of x minus y divided by 2, and then we used this formula in the numerator, and we wrote this as the limit of, for example, 2 times cos of these two angles added together times the sine of, for example, this angle minus this angle, and then divided by h. And usually what that gave us was basically, over here we usually got h divided by 2, and then sine h divided by 2, and then we used this 2 over here, and we wrote this as, for example, the limit of sine of h divided by 2 divided by h divided by 2 as h tends to 0, and that is equal to 1, and then that times, for example, cos of some angle as h tends to 0, and in the limit we got some answer over here. So that's how we solve this kind of problem. But right now the problem is that these two functions have to be basically essentially multiplied together, and that formula for sine x minus sine y gives you a way to get a product of two trigonometric functions with some combination of these two angles over here, and then you could solve the problem. But right now, as this is, as basically this problem as the problem stands here, basically what we have is basically sine raised to the power of some x minus sine of, for example, y, which is something that I have no formula for. I have to somehow know what is sine raised to the power n of x, and this is not sine squared x, this is not sine cube x, this is sine raised to the power n of x. So I need to find some formula for this one first. Now, in such cases where you want to find some formula for some situation like this, it's one way that you can solve this kind of problem. You want to know what is sine raised to the power n of some angle, for example, x. You want to find, for example, what is sine raised to the power n of x. Now, x could be any angle. It could be x plus h, it could be 2x, it could be 5x, it could be 5x plus 5h, or whatever it might be. And if I call this y, for example, now of course you know that basically if n is equal to, if n is equal to 1, then basically this becomes y is equal to sine x. Then d by dx of basically then dy by dx, which is d by dx of basically sine x, is equal to cos x. So that is for n is equal to 1. Now what I'm doing here is actually I'm trying to find some sort of rule for the sine function. I want to know, for example, what you can do. I mean, logically what you would think is that, okay, so I'm going to see what is going to be the derivative of sine raised to the power n of x when n is equal to 1, for example. And then what is, for example, and now if n is equal to 2, then y would be equal to sine squared x. And let's see what the derivative of that is. And the derivative of that is basically, you can write this as basically sine x times sine x, right? And so basically dy by dx is equal to d by dx of basically sine x times sine x, which you can use, for example, the product formula, u times v whole prime is equal to u prime times v plus uv prime, for example. And so you can write this as basically u prime, which is cos x times sine x plus sine x times the derivative of the second function cos x, which is equal to 2 times sine x cos x. So when n is equal to 2, then the derivative of sine squared x is equal to 2 times sine x cos x. Now let's see what happens if, for example, your n is equal to 3. Okay, and of course this process can be very beautifully coupled with basically something called the principle of mathematical induction. And using the principle of mathematical induction, then we can prove that, for example, d by dx of sine raised to the power n of x is such and such. It's actually a very, I mean, clever way of proving something. We will get to that in just a few moments. So now if n is equal to 3, then your y is going to be equal to sine cube x, which you can write as, for example, sine x times sine squared x. Sine x times sine squared x. And so then dy by dx is going to be equal to d by dx of sine x times sine squared x. And, well, of course, then again you can use this formula we can write it as basically cos x times the derivative times basically this function over here, sine squared x, plus the first function sine x times the derivative of the second function, which is the derivative of sine squared x. We calculated that here to be 2 times sine x cos x. 2 times sine x cos x, which is equal to cos x sine squared x plus 2 times sine squared x cos x. Sine squared x cos x. So 2 times sine squared x cos x plus sine x plus cos x sine squared x. Now it seems that, and of course these are the same thing, so this is basically 3 times, if you write this as, let me write this properly, so this is sine squared x, this is sine squared x cos x, right? Now, sine squared x cos x plus 2 sine squared cos x is equal to 3 times sine squared x cos x. So when n is equal to 1, the derivative of sine x is basically cos x. When n is equal to 2, the derivative of sine squared x is 2 times sine x cos x. Right? So that you could say that your n comes over here. So that means that if you have sine raised to the power n of x, then over here you can write your n comes over here because there is a 3 over here as well, right? And there is a 2 over here and there is a 1 over here as well. So you can say that d by dx of sine raised to the power n of x is basically your n comes over here, and then you have sine x raised to the power n minus 1, raised to the power n minus 1, and then you have cos x raised to the power basically, I'm sorry, n minus 2, because sine x is over here. If you have basically, if n is equal to 1, then 1 minus, no, not that. So you could say that, for example, you have basically, you have sine x and cos x over here. Now when n is equal to 3, you have sine squared x, so that is n minus 1. That is raised to the power n minus 1. And cos x is raised to the power n minus 2, right? So now it works here. Now let's see if it works here. Over here, when n is equal to 2, then 2 minus 1 is equal to 1, meaning that sine x raised to the power 1, and 2 minus 2 is equal to 0, doesn't work. Cos x is basically raised to the power 1 because it's present over here as well. So you can write it as basically cos x and sin x raised to the power n minus 1. So now it works here as well, meaning that you have n times basically sin x raised to the power n minus 1. So if you have 2 minus 1 is equal to 1, so you have sin x raised to the power 1 here, and then cos x. And over here, if n is equal to 1, so you have your n over here, which is a 1 over here multiplied by this. And then you have sin x raised to the power n minus 1, n minus 1 is equal to 0. So sin x raised to the power 0 is equal to 1. So here you can write sin x raised to the power basically 1 minus 1, which is 0. Then this whole thing becomes 1. And then you have cos x over here as well. So that's basically, that seems to be the formula. That seems to be the formula for d by dx of sin raised to the power of raised to the power n of x. Okay. Now, what we need to do is we need to basically use the but at this point, basically this formula has worked for n is equal to 1, for n is equal to 2, and n is equal to 3, and you could probably even set n is equal to 4 and calculate your derivative, and it might even work for 4, it might even work for 5 and 6 and so on and so forth. But there is no way to make sure that this formula is going to, even if it works for basically in the case of, for example, in the case of 10, 15, even 20, even 1,000 cases, if you just sit and try, for example, 1,000 different cases, and if it even works for 1,000 different cases, there is no way to make sure that it's going to work for every possible case. And even if you basically worked on this one single problem your whole life, you couldn't possibly get to the end of the numbers. So there has to be some way to make sure that this formula is going to work for all possible values of n. Right? So that way is basically called the principle of mathematical induction. So what that means is that in the principle of mathematical induction, we show that basically some formula, for example, works for example, p is equal to 1. That formula works for p is equal to 1. Meaning that, for example, we need to show that, for example, for n is equal to 1, this formula works, which is something that you can simply show. We have already done that. And then one more thing meaning that the formula works for n is equal to 1. And then moreover, there is one more thing here that you need to do, and that is basically, you need to basically show that, basically what you formally or usually do in this principle of mathematical induction, you then assume that basically the formula works for some, for example, for some n is equal to k, for example. For some n is equal to k, we assume that it works. And then we prove that, the formula works for basically n is equal to k plus 1. So what that means is that if suppose that it works for k, and the next case after k would be, of course, logically k plus 1. And it doesn't really matter what this k is. Whatever that k is, the formula is going to work for k plus 1. And then you can do the same thing over and over and over again. So if you assume that the formula works for some k, and then if the formula works for some k plus 1, then you can make sure that the formula works for every possible case. And then that's basically how the principle of mathematical induction works. It's essentially something like you have basically an n number of books, and you have put those books on their edges, right? N number of books all the way up to here. These are all basically n books, and well, a large number of books. So these books basically are arranged in such a way that if you push this first book over, it will fall over the second book. And the second book falls over the third book, and the third book falls over the fourth book. And in the same manner, logically, basically, if you push the first book over, then the second book falls down, the third book falls down, the fourth book falls down, and as a result, the last book will eventually fall down. So now, in order to basically simulate this same situation in mathematics, what I'm going to do is that I'm going to show that the first book will definitely fall down. That's basically this part over here. And then I'm going to show that as a result of each book falling down, the next book is invariably going to fall down, meaning that if the formula works for any k, it's going to definitely work for k plus 1. What that means is that if any book over here falls down, then invariably the next book, the book after that, is going to fall down. And that means that all of these books are eventually going to fall down, and the last book is going to fall down. That's called the method of mathematical induction. So what that means is that now we can basically do the same thing for this formula to check whether it's actually going to work for all the, for example, integers. If you take n as integers, for example, for all, for example, positive integers, you could say. It depends on what you want to prove, really, but you can define n as being a positive integer. You could take n as being even all integers, negative integers, and 0 as well, and so. But every part that you want to prove, you need basically every, for example, if you want to prove it for positive integers, you have to prove it one time for the positive integers. And then if you want to prove it for the negative integers, you have, in another basically process, you have to prove it for negative integers. For 0, you have to prove it for 0, and so on and so forth. And then, of course, with the same logic, you could prove it for basically for all real numbers, for rational numbers and all real numbers eventually. That's basically how they prove things in mathematics, of course. So what that means is that now I know that basically my formula works in the case of these three n's, and based on this we kind of recognize some sort of basically I would say, for example, trend over here, and I'm kind of guessing that the formula is going to be basically this formula for all n's. So now the language that is used here, you need to pay attention to that, because the words have been used in a slightly different way in this basically in the language here. So it says that we we assert that it says that we assert that d by dx of sine raised to the power n of x is going to be equal to n times sine raised to the power n minus 1 of x times cos x. Okay, that's what I have written over here. Now, when we say we assert that this is the case, that doesn't mean that I'm really sure that this is the case. This just means that this is what I want to prove. The word has been used in a funny way, but that's how the language is usually used in mathematics. So you need to basically you need to understand in what sense the words have been used here. The words are kind of not used in the way that we usually use them in day-to-day language. Okay, so if you remember, I told you that we assume that, for example, we assume that this assertion is true for some n is equal to k, meaning that we assume that, for example, when basically n is equal to k, the formula works, and then basically then we prove that when n is equal to k plus 1, the formula will work as well. So now I'm going to do the same thing over here. So I want to now to assume that basically when n is equal to k, the formula works basically. So in order to do that, so what you need to do is that, so this assertion, which is just some you could call it conjecture as well. Of course, I'm not using the word conjecture right in this context, but it's just some sort of assumption that I'm making, okay? Meaning that I kind of know that the formula could be something like this, but I'm not really sure about it. Meaning that I'm not sure that I know that the formula will work for n is equal to 1, for n is equal to 2, for n is equal to 3. But I don't really know if it's going to work if n is equal to 4, or if n is equal to 5, and so on and so forth. Okay? So now I can say that let the assertion be true for some n is equal to k. For some n is equal to k. And that is basically d by dx of, the meaning of this is d by dx of basically sine raised to the power k of x is equal to basically, over here we said that n times basically sine x raised to the power n minus 1 times cos x. So over here I can write k times sine of basically sine raised to the power k of x times cos x. Of course, this is k minus 1. So k times sine raised to the power k minus 1 of x times cos x. Now what you need to do is that, so over here I can call this basically in the context of basically in the context of the principle of mathematical induction, I call this P of k, okay? And of course I need a P of 1 as well. P of 1 is basically, I need to show that basically for n is equal to 1, the formula does work, right? And this is basically where I have shown that basically the formula works for n is equal to 1. So I can call this P of 1. So P of 1 is true, right? And of course I have assumed that P of k is true. Now I have to prove that P of k plus 1 is true, right? So now if I write based on this, if I write d by dx of sine of k plus 1 of x, it's going to be equal to, basically based on my assumption, sine raised to the power k of x is supposed to be k times sine raised to the power k minus 1 of x times cos x. So then if I have d by dx of sine of k plus 1 of x, then it has to be I could write this as d by dx of basically sine x times sine raised to the power k of x. And if you multiply these two together, you will get sine raised to the power k plus 1 of x. And now we can, of course, we can calculate this derivative, meaning that I can use the u times v whole prime, which is equal to u prime times v plus u v prime, in order to calculate this. So I can write this as basically the derivative of this is cos x times sine raised to the power k of x you can write this based on the of course times the second function, which is sine raised to the power k of x, and plus the first function, which is sine x, times the derivative of the second function. The derivative of the second function is sine raised to the power k of x is equal to this thing over here, which is k times sine raised to the power k minus 1 of x times cos x, which is basically equal to cos x sine raised to the power k of x plus, now here you have sine of x times sine raised to the power k minus 1 of x, so this is going to be sine raised to the power k of x times k times cos x. So I can take sine raised to the power k of x cos x out. I can take sine raised to the power k times cos x, sine raised to the power k times of x times cos x. I can take that out and write this as 1 plus k, right? So that's 1 plus k times sine raised to the power k of x cos x. So what that means is that, so we assume that over here P of k was basically P of k, which I assume that P of k is true. So we said that P of k was d by dx of sine raised to the power k of x was equal to k raised to the power sine of k minus 1 of x times cos x. Now if P of k plus 1 is supposed to be true, it's supposed to be like this. So this is of course all equal to d by dx of sine of k plus 1 of x, right? So based on this P of k plus 1, d by dx of sine of k plus 1 of x, wherever you see k over here, you have to put k plus 1, meaning that this becomes k plus 1 times basically sine of k plus 1 minus 1 is equal to k. So sine raised to the power k of x times cos x. And that's exactly the same thing. So here you have 1 plus k times sine raised to the power k of x times cos x. So I can call it, so I can say that therefore p of k plus 1 is true. So now what we have done is that we have shown that p of 1 was true, p of k was true, p of k plus 1 is true. That means that basically P, which is the statement that I wanted to basically prove, is going to be true for all cases of n. Now basically what this means that this is going to be true. So over here you can write hence by mathematical induction, d by dx of sine raised to the power n of x is equal to n plus, basically n times sine raised to the power n minus 1 of x times cos x. So that is basically what we proved by the principle of mathematical induction. And that's basically what we were actually looking for. We were looking for the derivative of sine raised to the power n of x is equal to n times sine raised to the power n minus 1 of x times cos x. So that is that. So now the next question that we have here is question number 21, I suppose. This was number 19. I'm sorry, number 20 is the next one, which we will do in the next video.